temporal filtering, which you do it in time filtering, and spectral filtering, which reverse, and that's only in audio and voice processing, which you actively filter, but in frequency domain. So you like convolution, do convolution in frequency domain. And it's not called filter anymore, it's called lifter, as an anagram of filter. It gets kind of funny. But for now, just know that whatever it is in time domain, and this is something you will see later on down in DSP and communication, is that in time we refer to it as temporal, in the frequency refer to it as spectral. So temporal power, spectral power, right? So there are 3 taus, 10, 20, and 40, and I avoid using the rect pulse because I want to show you guys this other way of doing it. It's logical indexing. Somebody did brought that up the other day, and this is a rather clever way and get you to design a more arbitrary function. With this, you can design any type of function provided that you know, like the indexing. Well, if you do rect pulse, it's strictly rect pulse. If you do this, then it can be any arbitrary shape, right? So this is my FFT parameter, and this is my tau is equal to 10. All right, so tau is equal to 10, this width, and then this is the Fourier transform. I listed the 1 over tau, 2 over tau, 3 over tau, negative, and so on. That's 1. If you get these graphs, then you should expect your lab grade to be like 5 or even above 5, like 6 if you type in the report well. So it's all about code polishing. You get a 5 full score if you have the right graph, but if your code is absolutely polished, meaning you put a lot of hard work into organizing the graph, organizing the code so that it's easy to read, it'll be at least a 5.5 to 6. That's extra points are bonus, right? By polishing, I mean your code contains no error and you label your graph like this along with the axes, provide extra information. So I don't have to look at what graph this is, what are you trying to plot, so that these are detailed and self-explanatory, and that'll be great. That'll be very helpful to me. Okay, so this is tau 20, and this is the overlay of all that. Okay, these are the phase. If you get this crazy phase, then you're correct. And this is the overlay of the system. So you have the black, which tau is equal to 40, and then the blue one, which is 20, and the red one, which is 10. The one thing I really want you to see and notice is that, so I'm going to go back and run this graph, and also pull this graph. Okay, from the get-go, you can see that the width here, the time width here, when tau is equal to 10, that if it's small in the time domain, that translates to a larger bandwidth. See this red line? It has a larger bandwidth. Or you can just look at these middle lobe over here, from -0 to 1 to 0.1. So it has larger bandwidth. If the time pulse is small, it has a larger bandwidth. So this coincides with the theory that what if this gets smaller and smaller? What if this width gets smaller and smaller? Then you can expect the red line, the red curve, to be bigger and bigger, right? Eventually, what's going to happen when it gets infinitely small, that it's just an impulse in the time domain? That translates to an infinite bandwidth, right? If this shrinks down to like just a narrow, thin toothpick in here, then this red line will be almost completely flat because it gets larger and larger, right? And that's why the Fourier transform of a pulse, of an impulse in time domain or frequency domain, if it's just an impulse, then the Fourier transform of that is just, it's just 1. You know, it's just 1. It just occupies 1 or whatever the amplitude this is. Okay, so it might be 1 times tau as per the amplitude of the time here. Okay, and if it's larger, you can see if it's larger, like this 20, then that corresponds to the blue graph over here. So if it's larger, then the bandwidth is decreased. The bandwidth is smaller, okay? And if it's even larger, like here, oh, sorry, this is 40. This is not 20. This is 40. So 40 divided by 2 is 20. So 40 has the narrowest bandwidth. So again, if you reflect on the duality property of Fourier transform, what if this gets infinitely large? What if the width of the time domains gets larger and larger? Then this will shrink down to like almost an impulse tube, right? This lab perfectly captures the duality property. If you have a time and its width is shrinking down to like 0, that means almost just like an impulse, then the band will be larger and larger, and eventually it will be a flat line. Whatever time frame we look at, eventually it will be a flat line. Okay. Conversely, if the spectrum, if the time width gets larger and larger, see that it's almost 1. So that at one point it gets large that all you can see is 1 and no 0. This will have shrink the spectrum. The spectrum here, the bandwidth will have shrink down to like 0, and eventually it will look like an impulse as well. See, this is the perfect capture of the duality property. So time decrease to like an impulse, frequency bandwidth increase to like infinite. Okay, time then expands to like an infinite time span, then the frequency bandwidth decrease to like almost like an impulse, reverse. Okay, any questions on this? All right. So this is actually a very, very good starter lab for that. Okay. All right. So today we're going to look at lab 3.